All right, section 2.3 on continuity. Here's some advice from past students. Okay, most of the functions we deal with in calculus are continuous. We need functions to be continuous to do a lot of the things that we do. And we can think of continuity as being able to draw the graph without picking up the pencil. And just to note that this justification wouldn't be counted as proving that something is continuous. That's just to give you sort of a conceptual idea. The true definition of continuity is that the limit is the same as the value of the function. So if we take a look at this graph right here, we can see that the graph is discontinuous at x equals 1 because the limit as x goes to 1 from the left does not equal the limit as x goes to 1 from the right. Discontinuous at x equals 2 because although the limit as x goes to 2 of f is 1, f of 2 is 2, so they're not equal. And continuous at 3 because the limit as x goes to 3 of f equals 2, which is also the value of f of 3. And just as a side note, and this isn't something that you'll ever be tested on, but if we are dealing with a closed domain, so you can see that this graph only exists from 0 to 4, we would consider the function to be continuous at x equals 0 and x equals 4 because the one-sided limits equal the value at those points. So that's only true for endpoints. Okay, so we can name our continuities or discontinuities depending on how they behave. So a removable discontinuity has just a hole. So if you can just make it a continuous function by filling in a single point, that's removable. And that's true whether the point is just completely missing or if the point has been moved to some other place up and down. We have non-removable discontinuities. So we have a jump discontinuity, an infinite discontinuity, and an oscillating discontinuity. Oscillating means if you were to graph this and keep zooming in towards x equals 0, you'll see the graph just continuing to go up and down, up and down, up and down, never actually reaching some point where it crosses. Okay, we can look at how to remove a discontinuity. So if you have a removable discontinuity, we can figure out just what that value is where it is discontinuous. So if we look at this function right here, there's a discontinuity at x equals 1 because if we plugged in 1, we'd divide by 0. If we evaluate the limit, we can see the behavior. So we can factor, cancel the factors, and then evaluate, and we get 3 halves. Which tells us if we make a piecewise function, x cubed minus 1 over x squared minus 1, for all values of x where x is not equal to 1, and 3 halves when x equals 1, the function would now be continuous. And that's continuous at x equals 1. Notice that there is still a discontinuity at x equals negative 1, which would be an infinite discontinuity, meaning there's no way for us to fill in that value. And here's the graph. And our point that we found, 3 halves, goes right there. If we have a function that's continuous, or multiple functions that are continuous, we can add, subtract, multiply, divide, and very importantly also is we can make composite functions that are also continuous. So f of x equals sine x, that's continuous. X squared is continuous, so sine of x squared is also continuous. And the intermediate value theorem. And just try to visualize what's going on here because this should make some intuitive sense. If a function is continuous between a and b, those are x values, then it takes on every y value between f of a and f of b. So we have a point when x equals a, another point when x equals b. If your function's continuous, there's no way you can go from a to b without taking on every y value in between. And there aren't many theorems in this class that we need to know word for word. This is one of those ones that we do need to know. So when I tell you the intermediate value theorem, you need to know exactly what it says. And when you see these conditions, you need to know that it's true because of the intermediate value theorem. And let's just look at an example that can use the intermediate value theorem. The question here is any real number exactly 1 less than its cube? Notice we're not asking what it is, we just want to know if it exists. So we could express this question as an equation. If the number is x, we want that to be equal to 1 less than its cube, x cubed minus 1. And we can rearrange that to make that 0 equals x cubed minus x minus 1. And so we want to determine if there's some value of x where x cubed minus x minus 1 equals 0. If we can show there's a value of x where this is negative and a value of x where this is positive, by the intermediate value theorem, there must be somewhere where it equals 0. F of 1 is negative 1, f of 2 equals 5. So since f is a continuous function, by the intermediate value theorem, there must be some value between x equals 1 and x equals 2 where the function is 0. And we can use our calculator to confirm this. And we can find that that occurs at 1.32472.